Hello, dear friends. Now we will see our next online lecture 9 on chapter 3 D block element for our chemistry paper first. Now in this lecture we will learn about magnetic properties. Magnetic properties is shown by all the transition elements. So what is magnetic properties? Magnetic properties, you know what is magnet. So magnetic properties of D block element shows two types of substance, magnetic substance, that is paramagnetic and diamagnetic. So this paramagnetism and diamagnetism are depends on pair or unpaired electrons. If if the d orbitals are incompletely filled, that is if they have unpaired electrons, then they are called as paramagnetic. Okay, now if the transition elements have all the completely filled d orbital, it means there is all paired electrons, then these substances are called as diamagnetic. So I hope you have cleared that which substance are paramagnetic and which substance will be diamagnetic. It depends on pairing and unpairing of electrons. So if electrons are paired, then they are called as paramagnetic, and if all the electrons if electrons are unpaired, then the substance are called as paramagnetic, and if the electrons all are paired, then they are called as diamagnetic. So it depends on the pairing and unpairing of electrons. So see, d block elements possess magnetism, and this magnetism is due to the motion of electrons. So motion of electrons are of two types, that is spin motion and orbital motion. So electrons shows two types of motion, spin motion and orbital motion. So now let's see what is spin motion and what is orbital motion. See in this picture, what is spin motion? See, when electron rotate in its own axis, see this one, when electron rotates in its own axis, this is the axis of this electron. Okay, this is the axis of this electron. So these electrons are revolving in its own axis. Okay, rotating in its own axis. So this is called as spin motion. Now what is orbital motion? Orbital motion means, you know, atom is present in circular manner, and there is in center a nucleus. Nucleus is a positively charged, and out of nucleus the electrons are revolving. Okay, electrons are revolving. So see in this picture, this is the central nucleus, and the outer electron are revolving at the axis of this nucleus. See, it is revolving around the axis of this nucleus. So this motion is called as orbital motion. This is just like revolution of earth around the sun. So revolution of earth around the sun is nothing but such motion is called as orbital motion. So this is the orbital motion, and these are spin motion. Okay, see, spin motion, and this is orbital motion, rotation around nucleus, and this is rotation around itself. This is rotation around nucleus. So electron motions are of two types, orbital motion and spin motion. Okay, so now you have cleared what is spin motion and what is orbital motion. So one electron are show two type of motion, that is orbital motion also and spin motion also. Okay, so due to this motion, there is a formation of some magnetic field around these electrons. Each electron is a small magnet. So each electron is a small magnet, and they have magnetic field due to this type of motion, orbital motion and spin motion. So now let's see next. So see here, spin motion, due to spin motion, this is a spinning of electron. So due to spin motion, there is a rise of spin moment or means spin magnetic moment. Okay, and orbital motion give rise to orbital moment or orbital magnetic moment. ठीक है. Okay, so this is orbiting electron, and this is spinning electron. So due to this spinning, there is a formation of spin magnetic moment. Magnetic moment is represented by mu. Okay, so this spinning electron give rise to spin moment, and this orbiting electron give rise to orbital moment. Okay, so spin moment and orbital moment give rise to a total magnetic moment of any electron. Okay, now next, see here, all the electrons, each and every electron of atom is act as a micromagnet. Each electron is act as a micromagnet. Okay, so the total magnetic moment of electron is considered as the sum of spin moment and orbital moment. Okay, see, this is the atom, okay, and this is the nucleus. So here these electrons are showing spin motion, okay, and also showing orbital motion. So spin motion give rise to spin magnetic moment, and orbital motion give rise to orbit magnetic moment. So addition of both of these give rise to total magnetic moment, total atomic magnetic moment. Okay, so what is the total magnetic moment? Formula of total magnetic moment will be, see, total or effective magnetic moment is equal to spin moment plus orbital moment. Okay, this is a spin motion and this one is a orbital motion. So spin moment plus orbital moment give rise to effective magnetic moment or total magnetic moment. So formula is mu effective means effective magnetic moment. Magnetic moment is represented by mu. This is a mu. So effective magnetic moment is equal to spin magnetic moment and orbital magnetic moment. So this is the formula for total magnetic moment or total effective magnetic moment of any atom. So remember this formula. Now next, so origin of moment. In this picture we can see how the magnetic moment is arose in any atom. So orbital magnetic moment, see, this is the electron revolving around this nucleus, okay. So when this electron are spinning or revolving around its own axis, give rise to spin magnetic moment, and when this electron is revolve around this nucleus, then it give rise to orbital magnetic moment. Okay, so the total magnetic moment is equal to the orbital magnetic moment plus spin magnetic moment. So this is the total magnetic moment of atom arise due to the spin motion and the orbital motion, okay, of electron. This is a part of quantum mechanics. Okay, so this is the origin of magnetism of any atom due to the spin motion of electron and orbital motion of electron. Okay, now next, see the orbital motion of unpaired electron in d orbital is squeezed by surrounded electron. So you know all the metals of d block element are forming complex by ligands. When ligands and metals are combined with each other, they form what? Complex compound. Complex compound are formed by this coordinate bond between ligands and metals. So when this metal see, when this metal is surrounded by these ligands, this ligand quenched the orbital motion. Quench what? Orbital motion of the unpaired electrons. Okay, see, quench means cancelling. Quench means cancelling. Quench means cancel. So see here, again we will see, when metal form a bond with this ligand is surrounded this metal from all side. See, in this way there is a formation of complex. The ligand may be 4 times or 6 times around this metal. So due to these surrounding ligands, the orbital motion of unpaired electron get quenched. Quenched means cancel. So orbital motion of electron get cancelled, and hence the total magnetic moment is only depend on spin magnetic moment of any electron, because orbital magnetic moment is get cancelled here. Okay, orbital motion is quenched due to the ligands. That's why the total magnetic moment of any complex compound is just depend on spin motion of electron. So the formula for total magnetic moment, that is mu effective, is given by under root n in bracket n plus 2. This under root, see the formula, see, mu effective means effective magnetic moment is given by this under root n in bracket n plus 2. This is the formula for spin motion of electron, spin magnetic moment. This is formula for calculation of spin magnetic moment of any electron. So here the effective magnetic moment is only depend on spin magnetic moment of electron, and we will use formula only, spin only formula. This formula is called as spin only formula, because orbital magnetic moment is cancelled here due to the surrounding ligands. So what is n here? Where n is the number of unpaired electron. N is number of unpaired electron. So magnetic moment is expressed in Bohr magnetons. Bohr magneton means Bm. Bohr magnetons is the unit of magnetic moment. Okay. So now how we can calculate the magnetic moment of effective magnetic moment of any atom by using this spin only formula. So see in this picture, if we want to calculate the magnetic moment of this copper sulfate pentahydrate. So in this, the copper is present in Cu2 plus state. So in Cu2 plus state, copper shows D9 configuration. So copper shows D9 configuration. Okay. So in this D9 configuration, there is only one unpaired electron. So n is equal to 1 here. So see this formula. Mu effective is equal to under root n in bracket n plus 2. So here n is equal to 1 because there is only one unpaired electron. So we will put 1 in place of n. So see here, n is equal to 1. That's why under root 1 in bracket 1 plus 2. So the answer is 1.73. So the magnetic moment of this copper sulfate complex is 1.73. So in this way we can calculate the magnetic moment, effective magnetic moment of any complex compound. So see here, when there is one unpaired electron, the magnetic moment will be 1.73. When there is two unpaired electron, the magnetic moment will be 2.83. When there is three unpaired electron, the magnetic moment will be 3.88. So on. Okay. So this is a calculation of magnetic moment by using this spin only formula. And this magnetic moment is expressed in which unit? That is Bohr magneton. Bohr magneton is written as capital B and capital M. So next, now if you want to see a video on magnetism in atoms, then we will see this video on YouTube.
Explain the atomic origin of magnetism. We know that certain materials behave like a magnet without any influence of external magnetic field. And certain materials behave like a magnet only when an external magnetic field is applied on them. So why is it that some materials behave as a permanent magnet, and some materials show the property of magnetism only when an external magnetic field is applied on them? To understand this, let's analyze the material at an atomic scale. We know that an atom consists of nucleus, surrounded by electrons that revolve around it. And the electrons and nucleus also rotate about their own axis. We also know that the flow of charge indicates the flow of current. And when a current flows through a circular coil, magnetic moment gets induced in the coil, in the direction given by the right-hand thumb rule. Similarly, in an atom, the rotation of nucleus and the revolution and rotation of electrons indicates the flow of small currents in them. This flow of current induces magnetic moments. The resultant of all the magnetic moments gives the net magnetic moment of the atom. Now, if all the magnetic moments induced in the material are in the same direction, then the material behaves like a magnet without any application of external magnetic field. But if all the magnetic moments induced in the material are in different directions, then they cancel out each other and their resultant becomes zero. In such cases, the material does not behave like a magnet. To make such materials behave like a magnet, we need to apply some external magnetic field on them. Thus, we can say that atomic origin of magnetism in any magnetic material can be explained by taking into consideration the magnetic moments of the spinning and revolving electrons and also that of the spinning nucleus. Mathematically, magnetic moment due to the revolving electrons is given
Now this is the animation of generation of magnetism in any atom due to electron motion. Okay, now see the magnetic moments. We have already discussed that it depends on number of unpaired electron. So if there is one electron, the answer of effective magnetic moment is 1.73. So it will be calculated by spin only formula, that is under root n in bracket n plus 2 Bohr magnetons. So if n means 2 electrons, if there is 2 unpaired electron, then we can solve this by putting n is equal to 2 and the answer will be 2.83. So this is the calculation of magnetic moment by using number of unpaired electrons. So see here, if there is one electron, the effective magnetic moment is 1.73. If there is 2 electron, the magnetic moment is 2.83. If there is 3 electron, the magnetic moment is 3.87. If there is 4 electron, the magnetic moment is 4.90. And if there is 5 electron, the magnetic moment is 5.92. So the magnetic moment is directly proportional to the number of unpaired electron. See, 5 electron means 5.92 magnetic moment. 4 electron means 4.90 magnetic moment. So it is said here that magnetic moment is directly proportional to the number of unpaired electron. If there is 2 unpaired electron, the magnetic moment will be 2 point something. Okay. If there is a 3 unpaired electron, the magnetic moment will be 3 point something. Okay. So this, due to this, it is said here that magnetic moment is directly proportional to the number of unpaired electron. So by knowing the number of unpaired electron, we can conclude about the magnetic moment of any atom. Okay, So this is the relation in between unpaired electron, number of unpaired electron, and magnetic moment. Now see, the next property of d block element is catalytic property. Catalytic property, you all know what is catalyst. Catalyst means the substance which is useful to increase the rate of reaction. This catalyst does not take part into the reaction, but just useful to speed up the reaction. To increase the rate of reaction, we use the catalyst. So catalyst not always enter into the reaction, but it just increase the rate of reaction. So all the d block elements, all the transition element are very useful in using catalyst. So transition elements have catalytic property. Catalytic property means they have property to increase the rate of reaction. So see here, this titanium trichloride TiCl3 is used as a Ziegler-Natta catalyst. This is the Ziegler-Natta catalyst. Okay, these are Ziegler-Natta catalyst. This is Ziegler-Natta catalyst. This Ziegler-Natta catalyst is useful for forming some polymers. Okay, so Ziegler-Natta TiCl3 is used as a Ziegler-Natta catalyst. V2O5 is used in the formation of H2SO4. Okay, this Fe is used in a Haber-Bosch process in making NH3. This is a Haber-Bosch process. So in this Haber-Bosch process, iron is used as a catalyst here. Okay, now next FeSO4 is used as a Fenton's reagent. Then PDCl2 is useful in a Wacker process. This is a Wacker process, and in this Wacker process there is a use of PDCl2. This is a PDCl2. So Wacker process is also useful for formation of these compound aldehydes or ketones. Okay, and V2O5 is used in the preparation of H2SO4. So this is a preparation of H2SO4. Here V2O5 is used as a catalyst. Nickel, platinum, palladium is used as a catalyst in hydrogenation process. You all know what is hydrogenation. Hydrogenation is addition of hydrogen on alkenes. We have studied this reaction in our first year also. Alkenes means C double bond C. When we add hydrogen H2 gas, we have to use nickel as a catalyst. So nickel, platinum, palladium, any one of these we have to use in this hydrogenation process. So when this alkene react with H2, we will get CH3 single bond CH3. So addition of hydrogen on C double bond C, you will get CH3 single bond CH3. This is called hydrogenation reaction. So this hydrogenation reaction require a catalyst, that is a nickel or platinum or palladium. So this is some catalytic properties of d block element. D block element shows very important catalytic properties in very important process in generation of some ammonias, or in important process like Wacker process, or in preparation of H2SO4, or in hydrogenation of alkenes. So these are the processes in which the transition elements are useful for showing their catalytic properties. Now last there is a last property of d block element is tendency to form complex. So all the transition element has a tendency to form complex. You know what is complex? Complex are like this. These are all complex. Okay, this is octahedral complex of cobalt, hexa amino group. Okay, this is octahedral complex of cobalt metal, octahedral complex of iron. ठीक okay, and this is a octahedral complex for this metal. M means metal. Okay, so these are some complexes, and these complexes are formed by forming a bonding in between this central atom cobalt and these ligands. Here NH3 is a ligands. Here this diethylamine is a ligand, NH2. These are ligands. Here cyanides are ligands. Here all these are ligands. These are called ligands, and the central atoms are called as metals. All these metals are transition elements. Okay, so these transition metals can form complexes. This transition element can form such complexes, octahedral or square planar or tetrahedral. So why these transition elements can form complexes? See, this transition element can form complex because of a small size of their metal ions. Because these give a high positive charge density to the metal ion, which help to accept the electron pair from ligands. Okay, so when these metal ions means these metal ions are in small size. When these transition metals form cations, their size again get decrease. This is decrease in size of metal ion. So when this size decreases, their positive charge density also increases. And due to increase in their high charge in density, this metal ion can easily accept the electron from these ligands. These ligands are nothing but they are electron donors. Ligands are called as electron donors. Okay, so due to the high positive charge on this metal ion, these ligands, due to the high positive charge on metal ion, this ligand can easily donate electrons to these small size cations, that is metal ions. So due to this high charge density, the ligands which has electron pairs, they can attract easily by this metal ion. Therefore these ligands can donate their electron very easily, and hence these transition metals can form complex very easily with other ligands. Now next next reason for transition metal for forming complexes, they form vacant d orbital. They have vacant d orbital. So due to having vacant d orbital, these d orbitals, these 5 d orbitals in each metal is vacant, not completely but partly they are vacant. So they can accept the electron pairs from these ligands very easily. So due to empty d orbitals, these ligands can donate their electron in empty d orbital easily, and due to these two reasons, these metals ion can form this complex compound and form coordinate bonds. This is the formation of complexes by this d block element. Okay, so due to these two reasons, first reason is small size of metal ion. Due to small size of metal ion, there is a high positive charge density, and due to this high positive charge density, they can accept electron pair from ligand very easily. Another reason for formation of complexes is they have vacant d orbital. You all know that there is in a d block element there is a partly filling of d orbital. Means in d orbital there is a presence of 1 to 9 electron. So there is some empty d orbitals. So these empty d orbitals can accept the lone pair of electron from ligands very easily, and hence the metal can form a coordinate bond with this ligand very easily. And in this due to these two reasons, these transition metals can form these types of ligands, complexes. So we can say here there is transition metals have a tendency to form complexes. So remember these two reasons. This is very important for examination point of view. So now we have studied about a d block element. So many properties we have discussed, First property we have discussed that they have metallic non-metallic characters. Then we have studied about their electronic configuration. Then electronic configuration we have studied their variable oxidation states. After that we have studied about their standard electrode potential. In that we have studied about reducing properties. After then we have studied the variation in colors of the compound formed by this d block element. After color we have studied about magnetic properties. Um, means these transition elements can form paramagnetic compounds or diamagnetic compounds. These paramagnetic and diamagnetic compounds are depends on pairing or unpairing of electron. If all the electrons are paired, then they are called as diamagnetic compound, and if all the electrons are unpaired, then they are called as paramagnetic compounds. After magnetic properties we have studied about their catalytic properties. Catalytic properties means transition element has a property to speed up the reaction. So in many important processes these d block elements are useful for increasing the speed of reaction. So in Wacker process it is useful. PDCl2, that is palladium, is a transition element. So PDCl2 compound are useful for speeding up the reaction of Wacker process. Then iron is useful in the Haber-Bosch process, that is a preparation of ammonia. Then we have studied about the tendency to form complexes. So there is a two reason of forming complexes of transition metals, that is this transition metals have a small size of metal ion. Due to the small size of metal ion, they have high positive charge density. Then due to high positive charge density, this metal ion can accept electron pair from ligands. So that's why ligand can easily form a bond between metal and ligands. Then due to vacant d orbital, they can easily accept the electron pair from ligands. So all these properties are very important in the examination point of view. So here we have completed the chapter 3 of d block element of our paper first, that is physical and inorganic chemistry. This chapter belongs to 20 marks, and it required 10 lectures. Now next 3 to 4 lecture we will revise whole chapter again. So don't worry if you have not understood anything, we will revise this chapter. Okay, so now it is a very nice experience of having online lecture with you on this d block element. I hope you have understood so many properties of d block element very well, and if not understood you can call me or you can ask a question on my mobile number on WhatsApp, or you can call me. So this is the ending of this chapter, and we will start in next videos the revision. Okay, so thanks for being with me. Kindly send your feedback about the lecture, online lecture preparation of from me. Okay, thank you so much.